All right, welcome to the deep dive. For you out there, you're a philosopher, right? So I think you're going to be really fascinated by this. We're going to dive into somebody you probably think you know, but maybe not in this way, Isaac Newton.
Yeah. I mean, when we think of Newton, we think of, gravity, maybe calculus, but we don't necessarily think of philosophy.
Right. We got this amazing entry from the Stanford Encyclopedia of Philosophy on Newton's philosophy, and it really digs deep into his philosophical contributions. As a philosopher, you know that these kind of distinctions we make now about science and philosophy weren't always so hard and fast back then.
Yeah, exactly. And the entry makes that really clear. It reminds us that the separation of science and philosophy really is a relatively recent phenomenon. In Newton's time, things were a lot more integrated. To understand him, we need to see him as a natural philosopher.
Okay, so our mission today is to uncover why Newton was such a huge figure in philosophy, not just science. We're going to see how his ideas not only transformed our understanding of the physical world, but also had a lasting impact on Western philosophy itself. He's influencing thinkers, really well. So, I think you're going to get a lot out of this. All right, let's unpack this a little.
To start off, I think it's important to put Newton in context. As the entry points out, the 17th century was a pretty tumultuous time in terms of philosophy. You had the decline of Aristotelianism and the rise of thinkers like Descartes.
Right. It was a time of huge intellectual change. Philosophers were wrestling with fundamental questions about, like, the nature of reality, how we know things, and even the methods we use to investigate the world. And Newton's right there in the thick of it, developing these groundbreaking mathematical and experimental methods.
One of the really interesting things from a historical perspective is how Newton was viewed in the 18th century. He wasn't just seen as this brilliant scientist, he was considered a canonical philosopher. Like, the entry mentions Johann Jacob Brücker's Historia Critica Philosophiae. That's a major work in the history of philosophy, and Newton has a prominent place in it. Same with D'Alembert's Preliminary Discourse. He's up there with folks like Bacon, Descartes, Locke, and Leibniz.
Wow. Yeah, we kind of forget that sometimes. Why do you think there's been this shift, this tendency to categorize him solely as a scientist?
Well, I think it really goes back to the 19th century and this idea of the scientist. The term itself was coined by William Whewell. This was part of this broader trend of professionalizing academic disciplines,
Hmm.
separating science from philosophy.
But now we're coming back to Newton's philosophical roots.
Right, and the entry makes a good point about this. Contemporary scholarship is increasingly recognizing just how deeply philosophical Newton's work really was and how much influence it had.
Yeah, and he was in constant dialogue with those big names, those philosophers we consider canonical: Descartes, Locke, Berkeley, Hume, Leibniz, Kant. To really understand their work, you have to understand Newton's philosophical ideas. It's all connected.
Absolutely. Okay, so going back to his context, remember that the term scientist didn't even exist back then. Newton and his peers were called philosophers, or to be more precise, natural philosophers.
All right, natural philosophy.
Yeah.
But this was much broader than how we think of science today, wasn't it?
Oh, yeah, definitely. It wasn't just about the physical world. It also included inquiries into, well, things like the vacuum, the human mind, even theological questions.
So when Newton called his book Philosophiae Naturalis Principia Mathematica, he was making a pretty deliberate philosophical statement, right? Not just a description of the book's content.
Absolutely. The title was a direct response to Descartes' Principia Philosophiae. Newton admired Descartes, but he felt Descartes' physics didn't really live up to the ideal of a physics based solely on geometry and math. He felt it needed more mathematical rigor.
So Newton's mathematical principles of natural philosophy were his way of saying, like, okay, I'm going to do this right, applying a more rigorous mathematical framework.
Exactly. And in a way, Newton was trying to do to Descartes what Descartes had done to Aristotelianism.
Yeah, and that's why it's so important to understand Newton within this broader tradition of natural philosophy, like the entry argues. Okay, let's move on to some of Newton's specific contributions, starting with his work on optics.
Yeah, his 1672 paper in Philosophical Transactions really shifted the focus from, the science of vision, like how our eyes work, to a more in-depth investigation into the nature of light itself.
Which leads to his famous prism experiments.
Right, those classic experiments where he shines sunlight through a prism and observes the spectrum of colors.
Yeah.
So through those experiments, Newton developed his doctrine of colors. And his argument was revolutionary. He said that colors weren't just modifications of white sunlight, which is what people had thought before, but they were actually original and connate properties of the light itself. Each color had a different degree of refrangibility, a different angle at which they refracted or bent when passing through the prism. Like, think of how each musical note has a different pitch, while each color of light bends at a slightly different angle.
That's so interesting. It seems so simple now, shining light through a prism. But it was a revolutionary idea. White light is a mixture of different colors, a truth revealed through experimentation.
And what's philosophically really interesting here is how Newton combines empirical evidence with philosophical argumentation. He's not just presenting results, he's interpreting them within a framework of substance and quality.
Right, and he even uses his observations to suggest that light might be a kind of body, suggesting it has a particulate nature.
Exactly. His reasoning went like this. Colors are fundamental qualities of light, and if light exists as rays, then those rays must have substance-like characteristics. Otherwise, how could you have qualities without a subject to, possess those qualities?
Yeah, it's like how we understand material bodies as substances with qualities. So if color is a primary quality of light, then light itself might be a substance.
Right, and this sparked immediate debate, as the entry mentions. People like Robert Hooke and Leibniz had criticisms.
They did. What did they think?
Well, both Hooke and Leibniz believed in wave theories of light, and they initially misunderstood Newton, thinking he was absolutely committed to the particulate view from the start. Hooke argued his wave theory could also explain the colors, and Leibniz, in a letter to Huygens, he even said Newton was claiming light to be a body propelled from the sun.
So Newton's scientific work, even early on, sparked these philosophical discussions about the nature of light, substance, quality. It's funny because the entry mentions that Newton really didn't enjoy these intellectual arguments.
It is kind of ironic. Even though he disliked these debates, his work always ended up generating them. And, thankfully he didn't completely withdraw from those discussions.
Okay, let's switch gears a bit and talk about Newton's relationship with Cartesianism. The entry talks about the influence of Henry Moore.
Right, Henry Moore. He was a major critic of Descartes. He didn't agree with Descartes' idea of identifying extension with matter. That concept of a plenum, where everything's completely full of matter. He also challenged Descartes on the interaction problem, how unextended substances like mind and God could interact with extended matter.
Yeah. So what was Moore's alternative?
So Moore's idea was that space is distinct from matter. It exists prior to matter. And he said all substances have a form of extension. Some are just penetrable, like mind and God are expended, but they can penetrate other substances.
Okay.
And Newton was really influenced by Moore. In De Gravitatione, the scholium to the Principia, the general scholium Newton, really adopts this Moorean view. He rejects Descartes and says space exists independently of objects.
He even says space is an affection of a being, just as a being. No being exists or can exist which is not related to space in some way. That's a huge claim. So space is fundamental to existence itself, even for things like God.
Right, exactly. Being somewhere in space is fundamental to existence. So that's a big difference from Descartes.
And they also disagreed on motion, right? Descartes had this distinction between ordinary motion, like simple movement from one place to another, and proper motion.
Yeah, proper motion, which was all about a body's relationship to the immediately surrounding matter.
Right. And Newton took issue with that.
He did. In De Gravitatione, he argues that Descartes' idea of proper motion doesn't actually work with his own laws of nature, specifically the law of inertia.
Oh, right, because inertia says a body stays in motion or at rest unless a force acts on it, not just because its spatial relationships change.
Exactly. So this led Newton to develop his own distinctions. Absolute and relative motion, true and apparent motion, mathematical and common motion, and, of course, the idea of absolute space.
Okay, so absolute space. That's a tricky concept. I mean, how do you perceive absolute space?
Right. So Newton argued that while you can't perceive absolute space directly, you can detect true motion. Specifically, you can detect acceleration, which is a change in motion, through its effects, like the famous rotating bucket experiment.
Ah, the bucket. Yeah, I've heard of that.
He used that to argue that the water's concave surface shows that it's accelerating. It wants to move away from the axis of rotation. And this true motion, this acceleration, it's independent of the bucket or anything else nearby.
So absolute space wasn't just some random idea. It was a way to explain how true motion works, and it was important for his laws of motion.
Yes, it also helped explain God's relationship with the universe.
Oh, right. And even though Newton had these groundbreaking ideas about space and motion, the entry points out that Cartesian ideas stuck around for a while.
They did. The philosophical world doesn't just change overnight. People were still very much into the Cartesian mechanistic view of the world.
Which takes us to the Principia itself. The entry talks about Halley's visit.
Yes, Edmund Halley. His question about a planet's orbit, assuming an inverse square law of attraction, got Newton to really buckle down and finally publish his work.
So Newton basically invented the field of mathematical physics, right? It wasn't really a thing before him.
Yeah, it wasn't. He was combining math and observation in this totally new way. He'd been talking about this geometrical approach in his lectures at Cambridge for a long time.
It was a major shift in how people thought about natural philosophy.
Right. It wasn't immediately accepted, though, just like his work on optics. It started a ton of debate about scientific methodology. It was so controversial that he added those reguli philosophandi, the rules of reasoning, in the second edition of the Principia. They were his way of explaining and defending his method.
Yeah, that makes sense. And another big difference between Newton and Descartes was the concept of force. Descartes thought everything happened because of direct contact, bumping into each other.
Exactly, impact. But Newton and Leibniz, actually, they agreed on this. They said force was central. He developed this concept of vis impressa.
Impressed force. What is that exactly?
It's basically an action exerted on a body that changes how it's moving. But it's not a property of the body itself. It's an action applied to the body. It stops as soon as that interaction ends.
Right, I can see how that was a pretty new idea for people back then. They were used to thinking of objects or substances causing things to happen.
Right. But Newton said that these transient actions, these forces, were the key to understanding motion.
And the really cool thing is that he defined force in a way that you could use math to describe it. He linked it to mass and acceleration with his laws of motion.
Right, and that was a huge breakthrough. By quantifying force, he could say that all sorts of different phenomena were governed by the same type of force. It was a big unifying idea.
Like when he showed that the force making the planet's orbit, the centripetal force, is the same type of force as gravity here on Earth.
Exactly. He unified celestial mechanics with terrestrial mechanics, all because he was thinking about forces in this abstract, quantifiable way.
That's amazing.
It really is. And of course, this led to his concept of universal gravitation, which said every object in the universe attracts every other object. It was a revolutionary idea, and it caused a lot of debate.
Yeah, I bet. Especially the action at a distance part. That must have been hard for people to accept.
It was. To try to address some of these concerns, Newton added those regulae philosophandi in the second edition of the Principia.
Right, the rules of reasoning.
Yes. And Rule 3 in particular sparked a lot of discussion.
It did?
Yeah.
What was so controversial about it?
Well, Rule 3 basically tackled the problem of induction. How do we go from observing things here on Earth to making claims about the entire universe?
Right.
So Rule 3 says, those qualities of bodies that cannot be intended and remitted, that is, increased or decreased, and that belong to all bodies on which experiments can be made, should be taken as qualities of all bodies universally.
Okay.
And Newton used this rule to justify his claim of universal gravitation. We see gravity working here on Earth, and we see it working between the Earth and the Moon. So Newton said this quality, the mutual attraction of bodies, must apply to all matter throughout the universe.
Okay, that makes sense, but not everyone bought it, right?
Right. People like Leibniz had a problem with this. They thought gravity might be what they called an occult quality, if it was some kind of inherent power working across vast distances without a mechanism to explain it.
Right, occult quality. They didn't like that idea.
No, it sounded too much like pre-scientific thinking. They wanted a mechanical explanation, the how.
Right. Okay, so let's talk about how Newton influenced other philosophers, starting with John Locke. They were friends, right?
They were, and Locke praised Newton in his essay concerning human understanding. He called him a master builder in the experimental philosophy.
Right. But Locke was a mechanist, wasn't he? He thought bodies could only interact through direct contact. So Newton's idea of universal gravity must have been a bit of a problem for him.
It was. Locke initially said it was inconceivable how bodies could affect each other across empty space just through attraction.
Yeah, that makes sense. So how did he resolve that?
Well, Locke ended up accepting universal gravity because of the evidence, but he maintained that we can't fully understand the mechanism behind it. He thought God must have added some extra powers to matter, powers that we couldn't figure out from our idea of what matter is.
Okay, so he accepted the fact of gravity, but said the how was still a mystery. a mystery that God solved, I guess.
Right. But this is different from Leibniz. Leibniz was really committed to this idea that any fundamental powers in matter had to have a mechanistic explanation, at least in principle.
Right, he had to understand the how. The entry then goes on to Newton's letters with Richard Bentley.
Oh, yes. Bentley wanted Newton's help to argue that the solar system shows evidence of God's design. The whole argument was based on the Principia.
So Newton was using his own work to support theological arguments.
Yes. He argued that the solar system's stability and complexity, the way everything worked together so perfectly, showed it couldn't have just happened by chance.
That's pretty interesting. But these letters are also known for what Newton says about action at a distance, right?
IR. Newton says, "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact."
So it sounds like he's rejecting action at a distance?
Well, it does sound that way.
Yeah.
But there's been debate about what he really meant.
Oh. So what are the interpretations?
Some scholars think he was rejecting the idea that gravity is a power inherent in passive matter itself, that matter is basically inert and needs something external to make it active. Maybe even divine intervention. He didn't want people to think he was saying matter could act on its own, like an Epicurean view of the world.
Right. So maybe Newton was a little uncomfortable with the implications of his own theory.
It does seem that way. But regardless of what Newton personally thought, his contemporaries, especially Leibniz, strongly disagreed with action at a distance.
Okay, so let's get into the Newton-Leibniz debate.
All right, so both Newton and Leibniz grew up in this philosophical environment where Cartesianism was really important, and both were focused on the idea of force. They knew each other's mathematical work, but their philosophical relationship really started after the Principia.
Okay, so what did Leibniz think of the Principia?
Well, he was critical. In his essay on the causes of celestial motions, he proposes a fluid medium as the cause of planetary motion. It was basically a vortex theory, and it kept with that whole mechanistic idea that things need to touch to interact.
So Leibniz was basically saying that Newton's attraction was just a word. It didn't explain the real cause, which he thought was this fluid.
Right. But Newton wasn't buying it. He said this fluid medium would mess up the planets' and comets' orbits. He argued that gravity itself was the direct cause.
So the big disagreement was about action at a distance. Leibniz was a hard no, and Newton was, well, he was more open to it.
Yeah, and this led to even more criticism from Leibniz. He called Newtonian gravity a perpetual miracle. He basically said that if you don't have a mechanism to explain how it works, it's like saying God just makes it happen all the time.
Like it's magic or something.
Yeah, and Leibniz said that even God couldn't make action at a distance happen because of the nature of matter. Matter is extended, it takes up space, and it can't penetrate other matter.
Okay, so how did Newton respond to that?
He basically said, hey, why are you so hung up on gravity? Other things can't be explained mechanically either. He pointed to hardness and V's inertia.
He's fighting back.
Yeah.
Saying, look, if you're going to call gravity an occult quality, then you have to call these other things occult qualities too.
Exactly. And this was all playing out in the famous Clark-Leibniz correspondence.
Whoa, right.
Yeah, Samuel Clarke was a big defender of Newton, so he got into it with Leibniz too.
And what were they arguing about?
Oh, all sorts of things. Leibniz argued that Newton's ideas could lead to materialism, and that Newton's God would need some kind of organ to interact with the world. He thought those were theologically problematic.
Yeah, I can see how that could be an issue for a theologian.
Right. And Leibniz also used his principle of sufficient reason to critique Newton's idea of absolute space. He asked, why would God put matter in one particular part of space rather than another if space is uniform?
Okay, I see the problem. If space is all the same, then God would need a reason to choose one spot over another.
Right. And Clarke responded by saying that God's will could be a sufficient reason, even if we don't understand why.
So Clarke's basically saying that God can do whatever he wants. He doesn't need to answer to us.
Exactly. They also argued about action at a distance, of course. And this time, Clarke took an even stronger position than Newton, saying action at a distance is a logical contradiction, not just improbable.
Wow, that's pretty bold. It sounds like Clarke was taking Newton's ideas even further.
He was. And all of this shows how much Newton's ideas influenced philosophical debate. They shaped the discussions about space, time, causation, and the nature of reality for the entire 18th century.
It's incredible. And speaking of influence, let's talk about the impact Newton had on the wider world of philosophy.
Yeah, it's huge. The 18th century really can't be understood without taking Newton into account. You've got the ongoing debates between the Newtonians and the Leibnizians.
Right, and the Newtonian movement in Britain, the experimental philosophy.
Exactly. And, thinkers like Berkeley and Hume had really interesting reactions to Newton's work.
Berkeley was pretty critical, wasn't he?
He was. He didn't like those abstract ideas like absolute motion and force. He thought they were incoherent. Instead, he developed his idealist philosophy where everything's ultimately based on perception and the activity of minds. And he thought causation was all about God and spirits interacting.
Okay, so Berkeley's response to Newton was to develop a whole different system. What about Hume?
Hume was also an empiricist, but he wanted to reinterpret Newton's ideas in a way that avoided this idea of force as a power that we can really know. He even mentions Newton's idea about an ether to explain gravity, that medium that Newton wasn't so sure about. He even quotes Newton on this.
So he's trying to ground Newton's ideas in what we can actually observe.
Exactly. And then, of course, you've got folks like D'Alembert and Euler on the continent. They were big mathematicians who also debated about Newton. And, of course, there's the French reception of Newton. Voltaire was a huge fan. And then there's Émilie du Châtelet.
Right, du Châtelet. She's fascinating. What was her take on Newton?
Well, she agreed that gravity was a good way to describe how things work, but she wasn't sure if it was an essential property of matter. She thought maybe there was some kind of medium involved. And like Leibniz, she used the principle of sufficient reason to critique Newton's idea of absolute space. She also thought that maybe God wouldn't just randomly place matter in one spot. Then you've got Euler, who argued for absolute space. He said you need it to define a straight line for the law of inertia.
Right, I see.
And then you have Kant. He's really interesting. He was deeply influenced by Newton. He called gravity the foundation for general cosmology and argued that it involved action at a distance. He said, I will boldly assert that if there were no Newtonian attraction, I would have to give up entirely the hope of ever understanding the constitution of the heavens from mechanical laws. He actually puts that in his the only possible argument.
Wow, that's quite a statement. So Kant starts with Newton, but he also ends up critiquing Newton, right?
Yeah, he does. In his critique of pure reason, he critiques absolute space, and then he tries to kind of bring it all together in the metaphysical foundations. He reinterprets absolute space as an idea of reason, which is very interesting.
Yeah, that's a lot to unpack. So even centuries later, Newton's ideas are still relevant. They're still shaping these big philosophical discussions about the nature of reality, how we know things, the limits of human knowledge, and the basic laws of nature.
Exactly. He was doing so much more than just science. He was a philosopher at heart.
So, for those listening who are philosophers, I hope this deep dive into Newton's philosophical side has given you some new insights. It really shows how interconnected science and philosophy are, especially back then.
It does. And it makes you think, what do we lose when we separate these fields too much? And what does it mean to think about those big questions that both scientists and philosophers are trying to answer? Questions about the nature of reality and the limits of human knowledge.
Yeah, that's a great question. And maybe Newton can help us answer it, even all these years later. Well, that's it for this deep dive. Thank you so much for listening. I hope you'll explore some of these ideas further on your own.